We're told here that we have a box which is resting on a table and the box has weight W, and that's going to be acting vertically downwards. At the same time as that, there is a normal reaction, so there's a normal contact force between the box and the platform, which is going to be acting vertically upwards. And we're told that that normal contact force has magnitude Kw. So in other words, it's equal to Kw when the box is moving upwards with an acceleration of A. Okay, now we need to know what the mass of the box is, and obviously we don't know that, so let's just assume that the box has a mass of m kilograms. In other words, its weight is going to be mg, and I might be using that later. Okay, so we now know that the acceleration is vertically upwards. I'm going to use Newton's second law in an upward direction because that's where the acceleration is. Acting upwards, we've got the reaction. Acting in the opposite direction, we've got the weight. So R minus W must equal the mass times the acceleration. Okay, let's start substituting. Instead of R, I can write KW. And I'm going to leave that as W. Now the mass, I don't actually know, but I can rearrange this and realize that m is actually just equal to W divided by G. So over here, I can use my mass as W over G multiplied by A. Okay, so if I factorize this side, so I've got W multiplied by K minus 1 is equal to AW over G. And the question asks me to show that A is equal to G times K minus 1. Well, if I multiply both sides by G, I've got GW times K minus 1. And if I then divide both sides by W, I've got W, and that equals A. And I can see that the W's cancel each other out, and there's my expression. In the next part, we've got a slightly different situation because it's now accelerating downwards at 2a meters per second. And we know that this 2a, because we know from up here that a is equal to g brackets k minus 1, the acceleration now must be twice that. In other words, it's now 2g brackets k minus 1. Okay, so let's apply Newton's second law here. The weight hasn't changed. The weight is still mg. Normal reaction, though, will have changed because the acceleration is different. Okay, so let's apply Newton's second law in a downwards direction, which is the direction of the acceleration. So the combined force, so the overall force acting downwards is W. So again, we've got W minus R is equal to the acceleration. And the acceleration now is 2g times k minus 1. Okay. And that's multiplied by the mass, and the mass is still W over G. Okay, the G's cancel each other out, and we're left with W minus R is equal to 2W times K minus 1. If we remove the brackets, W minus R is 2WK minus 2W. And if we just move R to the right now, on the left-hand side, we're going to have W plus 2W minus 2WK. Now, if we simplify that, we've got W plus 2W, that's 3W minus 2WK is equal to R. Factorising the left-hand side, we've got W multiplied by 3 minus 2K is equal to R, which is the required expression. What we now have is the situation where we've got our box on its platform and it's accelerating downwards. The weight, which is acting in this direction, is W, and acting upwards, the normal reaction is W multiplied by 3 minus 2K. Now, for this to be a realistic situation, this value here, the 3 minus 2K, must be positive. In other words, 3 minus 2K is greater than 0. If we move our 2K over there, we've got 3. K then is less than 3 over 2. So K is less than 3 over 2.